Okay, good morning. Welcome to
Remember 615.
FamilyMath615. So this is a new series of posts by Craig Kaplan that I saw thanks to a post by our friend Patrick Connor. And it's about tilings. And we've done a couple projects on tilings before, right?
Yeah.
Yes.
So I don't want to go into a lot of details. I just want to study one of the near tilings here. But what he's talking about is what sorts of different shapes can make tiling. So here's a shape. So he's starting out by asking the question, can you surround the shape with itself? And what do you think is going on here?
Well, he's looking at some ways to do it.
Okay.
And then he's looking for the ways if it can be tiled or not.
Or like if the shape can be completely surrounded by shapes that congruent shapes to it.
Okay, yeah, so we've got to go up a little bit to see. So here's the problem of surrounding a polygon. You see that?
Yeah.
So let S be a shape in the plane. Under what circumstances can S be surrounded by transformed copies of itself? Specifically, I'm looking for a collection of copies with the following properties. S, which I guess is the yellow polygon, and its copies form a single connected blob in the plane containing no internal holes. Every copy of S meets S in at least one point. In other words, every copy is doing useful work as part of the surrounding. And every point of S is completely inside the blob. No point of S's boundary makes contact. Okay? So here's a visualization of the different ways a collection of copies might fail to make a surround, followed by an example of a successful surround.
All right.
Okay? So here's the shape, this sort of Tetris piece.
Right.
What's wrong with this one?
There's the hole on the inside.
Okay. Trickier one, what's wrong with this one?
Well, this piece isn't doing anything.
Yeah, but why do you need that piece?
Well,
You have to have it like touching the shape. You have to have it every copy of S meets S at least one point. So you
Okay.
have to have it touching for it to count.
Yeah, but if I take that one away,
But
Like,
you need to use all of them.
how many pieces do you need, do you think?
maybe you need to use, well, S has 1, 2, 3, 4, 5. S has 6 sides.
Okay.
It's the L shape, but you're using 5.
Okay. So for some reason we seem to need to use 5, do you think? Or do you think we just had an extra piece here?
It sort of looks like we have an extra piece because down in the successful one, you only used 4.
Ah, okay. All right. So there we just seem to have an extra piece that wasn't helping. Hey, what's wrong with this one down here?
Well, I guess like it has to be completely surrounded, so this one doesn't. It's not helping.
Okay. So on that one, there's a corner open. So there actually is a little escape hole, even though it's just a
Yeah.
single point. The corner's open. And then what's going on with the successful one?
Well, these four of these shapes are covering this space here.
Okay. So we're looking to try to find something like that. And then what we're gonna study is this shape here. Okay. But first I wanted to show you a neat one down here that another mathematician found. Pretty cool, huh?
Yeah.
So we're going to look at this shape, and this is one that actually does not form a tiling, but you can see you have successfully surrounded the shape, right?
Yep.
And this shape is made from a square, an equilateral triangle, and a 30, 60, 90 triangle. So what we're going to do is we're going to learn how we can make this shape in Mathematica,
Yeah.
and then we're going to print out. Let's see, how many do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9 tiles, and just do some exploring with them.
All right.
Okay?
Yeah.
All right, let's move on to that.